we did a bunch of examples last time, but now let's do more. But before that, let me write down some of the properties of continuity. So properties of continuity. So make sure that you know the definition of continuity at a point, okay? And that you know how to write it, because that could be a question on the exam. That's very important, okay? All right, so properties of continuity. So suppose that you have a real number, so let K be a real number, and F and G, two continuous functions. Okay, at x equal a, then the statement is that if you have two functions that are continuous at a point, if you add them, you still get continuity. If you subtract them, you still get continuity, and so on and so forth. Okay? So the first one is if you multiply a function by a constant, it doesn't affect the continuity of the function. So then k times f of x is also continuous. At x equal a, and similarly, the sum or the difference of the function are continuous at x equal a. So sum of continuous is continuous, difference of continuous function is continuous. If you multiply two continuous functions, you get a continuous function, okay? And similarly with the quotient, the only difference is that you have to make sure that the bottom is different than 0, of course. So this is continuous at x equals a as long as g of a is different than 0. Okay? Because if both f and g are continuous, but it turns out that the function g happens to be 0 at a, then of course, when you look at the quotient, this is not going to be continuous because the quotient is not defined at a. Okay? So this property is, it's the same thing that we have for limits. So that means that continuity behaves well with respect to all of these operations. Okay? The algebraic operations that you like to do with functions, continuity behaves well. That's basically what we're saying here. We don't lose continuity. Okay, so because of this, now we have a bunch of functions that we can easily verify that they are continuous. So let me write down here a list of known functions that are continuous. So known functions that are continuous on their domain. So remember, last time we saw that most of the time, if you want to figure out when a function is continuous, it really just boils down to figuring out the domain of the function. So as long as you know how to find domain, you're good to go in most of the cases. All right, so first, polynomial functions. So polynomials, so that is functions of the form p of x equals an, x to the n, and so on. Okay? So any polynomial function is continuous because after all, a polynomial is just a sum of a bunch of power functions, okay? And each of these power functions, as you know, they are continuous, okay? And the sum of continuous function is continuous. So every polynomial is continuous. And rational functions. Rational functions. So remember, these are functions of the form p over q. And then, as long as q of x is different than 0. So rational functions are continuous on their domain. So all values of x for which the denominator is different than 0. Radical functions. So these are functions of the form n root of x. Okay? And all trigonometric functions, remember, this is continuous on their domain, so let me stress that, on their domains. Doesn't mean that they are continuous everywhere. So trigonometric functions And here we mean, the usual one: sine, cosine, tangent, cotangent, secant, cosecant. All of these functions, they are continuous in their domain, and exponentials and logarithms. And most of the functions that is just combinations of all of these functions, like addition, subtraction, quotient, and then I give you a theorem about composition. Okay? So almost every formula you can write is made out of these functions that I'm writing here. So it's very nice to know this, that we just have to find the domain in most cases. Exponentials, exponential, and logarithmic function. So that is a to the x, and it's a particular case because this one shows up a lot. Let me specify. So e to the x belongs here to this family, but just write it down because it's important. And then, as I mentioned last time, whenever we analyze a logarithmic function, I will just look at ln. Any other logarithm can always be written in terms of ln. Okay, it's just a constant times ln. So as long as you understand the natural log, you will be able to understand any logarithmic function. Okay, any questions on what's written here? Okay, so let's see. Example. Find the intervals where the function is continuous if there are points of discontinuity of discontinuities classified. Remember the two types of discontinuities. If you see that a function is not continuous at a given point, it's either removable or non-removable. Okay. And step number 2, the existence of the limit, is the one that tells you which type it is. So in this problem, I'm going to give you some functions. Tell me where they are continuous. If there are points at which they are not continuous, tell me what type of discontinuity we have. Okay. All right. So let's do x plus e to the x, then x minus 2 over x squared minus 4. Let's do 3 times tangent. And let's do let me put here
what does that replace?
3 times tangent. Okay, so here we have some function. Oh, let me give you another one. Okay, so here we have 5 functions. I want you to tell me where they are continuous, and if some of them happens to not be continuous at some points, then tell me the type of discontinuity. Okay, that's an answer for number 1. Anybody? Yes?
Order of numbers.
Very good. Why?
One is exponential, the other one's linear.
Uh-huh. And the other one is what?
Linear.
Linear. Good. And?
You're adding 2 continuous functions.
Very good. So this is the sum of 2 continuous functions. This is a line. There's no problem with lines. Okay? Remember, as what we just wrote above. Polynomials, this is a polynomial. Polynomials are continuous. Exponentials are continuous. The sum of 2 continuous is continuous. Right? And because each of these, the domains are real numbers, this function is also continuous for all real numbers. As easy as that. There's nothing to do here. It's just look at it and answer the question. Okay? No work to be done for number 1. So solution. Number 1, f of x is continuous everywhere. In other words, it's continuous on negative infinity to positive infinity. Do you understand the reason why? It's a sum of polynomial plus an exponential. Okay? All right. How about number 2?
The domain is negative infinity to negative 2, and 2 to negative 2 to infinity.
And what happens in between negative 2 and 2? So, for example, you are jumping 0, right? Can we plug in 0? Yes, okay. So the domain is, what's the domain for number 2? Just tell me the sentence. You don't have to tell me the interval notation. What's the domain for number 2?
X is equal to negative 2 or 2.
You say it's equal or it's not equal? It's not equal. Very good. So the only problem that this function is that you cannot plug in 2 or negative 2 because any of those values will make the bottom 0. Anything else is okay, right? So the domain is all real numbers except 2 and negative 2. Now, okay, so let me write it here and then I'll show you how you can write that in interval notation pretty quickly. So this is the function. So remember, this is a rational function. So we know rational functions are continuous on their domain, right? So we just have to find the domain of this function. And for that, there's something that we don't want. What we don't want here?
2 or 0.
We don't want the bottom to be 0, right? So we don't want this to happen, right? So this happens whenever x becomes 0. I mean, whenever x is either negative 2 or positive 2, right? So that means any real number except these two guys are okay for our function. So if you are not sure how to write this in interval notation, my advice is just draw a picture and the picture will tell you exactly what it is. So here is negative 2, here is 2. We don't want these guys, we want everything else. So now you can see that you need to write 3 pieces, right? For example, you were telling me this one, you were jumping all of this. If you draw a little picture, the picture tells you exactly what to write, okay? So everything else is fine for us. So this picture here is negative infinity to negative 2, right? This one over here, what is it?
Negative 2 to 2.
Negative 2 to 2. Do you understand why I'm writing parentheses? Open circle means parentheses. We don't want those endpoints. And this one over here is 2 to infinity. And then we just want to put them together, so put the union. Okay? Just draw a picture. The picture tells you exactly how to write the interval notation. So this is where the function is continuous. So in particular, it means that we have 2 points of discontinuity, right? It's not continuous at negative 2, and it's not continuous at 2. We need to classify them. We need to say the type. So far, f is continuous on all real numbers except 2, negative 2. Just giving the interval notation here. So f is not continuous at negative 2 and 2. So let's classify them. Okay, how do we do this?
You find the limit.
We need to find the limit. And then what do?
We make sure that the value of the function is equal to the limit.
Well, we know that's not going to happen because we don't have continuity, right? I mean, the function is not defined at those points. So you find the limit. What do we do with that? So what conclusion do you draw from that? I mean, why are you finding the limit?
See if
Removable.
Exactly. So you try to find the limit. If you get a number, what's your conclusion? It's a removable discontinuity. If you don't get a limit, if you get infinity, or if you get that the limit doesn't exist, what's your conclusion? It's not removable. Remember, don't just tell me find the limit. Yeah, but what do you do with that? You need to know what to do with that. Okay? So we know that the function is not continuous at these two guys. Okay. So now let's see whether it's removable or not. How do we do that? Take the limit as x approaches -2 and see what happens. Take the limit as x approaches 2 and see what happens. Okay? All right. So let's analyze x equals -2. So for that, we're going to take the limit as x approaches -2 of the function. So I'm going to put the factor version already. So the function is x minus 2 over x plus 2 times x minus 2. Okay, so again, remember, when it comes to limits, it's always it's okay to simplify, right? So I'm just gonna do that, even though we don't need it right now, but I'm just gonna do it because it's easier to analyze. Okay, so here we're approaching -2. So what can you say about this limit? So we get a 0 in the bottom, right? What happens when you have a number divided by 0 in a limit? It's a type of infinity. But our job now is to decide what type of infinity this is. Which one is it? If anything. Why? How do you know that? We are approaching -2. We never specify a side. So at this point, you realize that you want to, there will be some type of infinity, or maybe it does not exist. Because you may have a different behavior around -2. Yes? The point is that definitely you're not gonna get a number because there's a 0 down here. You understand this? Now, if you want to really see what happens, you should understand that this is not enough. You need to look at side limits. Because otherwise, you cannot decide is it positive or is it negative infinity, right? It turns out that if you do it from the right, what's gonna happen? What happens if you do it from the right?
Positive.
You're gonna get positive infinity. And if you do it from the left, what's gonna happen? You're gonna get negative infinity. So what can we deduce about this guy? Does not exist. Do you understand this? So does not exist. This limit does not exist. Since limit as x approaches -2 from the right is going to be equal to positive infinity, and that's because x is bigger than -2, so x plus 2 is positive. Okay? So you're getting close to 0 with positive numbers, so 1 over very tiny numbers, they get very big in the positive direction. Since this happens, and if you do it from the left, again, this means x is less than -2, so x plus 2 is less than 0. So that means you're gonna get negative infinity. Okay? The bottom is getting very tiny, but with negative numbers, so this is gonna go down to negative infinity. Do you understand this? All right. So we have this, so that means that the limit itself does not exist. I mean, even if it was infinity or negative infinity, we still would say it does not exist. Okay? So the point is that what we have here is a non-removable discontinuity. We cannot fix this problem. Do you understand this? Okay. And what's another name that we give to this discontinuity? There were two names: jump or infinite discontinuity. Which one do you think it is? This is an infinite discontinuity. The condition is that one of the side limits at least give you infinity. Okay. The jump discontinuity is when you have the gap, which is when the side limits exist, but they are different. When you go to 3 here and then 2 over here, then there is a gap, there is a jump in your function. Okay, that's still not removable, but we call it also jump discontinuity. Anyways, so this means that at x equals -2, we have, or let me say, f has a non-removable discontinuity. Do you understand this? All right, so that was x equals -2. Now we analyze x equal 2. So again, we take the limit. So if you don't mind, I'm gonna go straight to this Okay, just reusing this line here, we know the limit of the function, play the same game, so it turns out that that's the same thing as, should be positive 2, 1 over x plus 2. Does everybody understand why I wrote 1 over x plus 2? You just do a cancellation, the same thing that we did above. What do we get for this limit? 1 over 4, so what does that mean? We have a removable discontinuity, right? Because the limit exists. So at x equal 2, f has a removable discontinuity. So the full answer to the problem is the function is continuous on this interval. So everywhere except 2 and negative 2. And at negative 2, the issue is non-removable. At 2, it's okay. It's a removable. It's continuous. Okay? All right. Questions? By the way, what this means is that if you're going to graph that function, the graph of that function is the same as this one. It's just that there is a hole. Where is the hole? At the point, what is it? 2, 1 over 4. That's the hole. So the graph of our function is the same as the graph of this function, which is 1 over x shifted to the left 2 units. But then you need to put a hole at the point 2, 1 over 4. That's how that function looks, our function. And it has a vertical asymptote at negative 2. Okay? As we saw here. When you approach negative 2 from either side, you get different infinities. So the function does this. Okay? Okay. Questions? So once again, if you're given a function by just a single formula like this, interesting. There was some time without this happening. Maybe I move the cable. So if you're given a function as a single, now I didn't move the cable. All right. There is a spirit touching the bottom.
Yeah.
Maybe. We don't know. Okay, anyway, so if you're given a function given as a single formula like these examples, the problem boils down to just finding the domain of that function. Okay? Whatever the domain is, that's where the function continues. Now, the points that you exclude from the domain, there are discontinuities at those points, so you need to find the time if you are asked to find it. How do you do that? Attempt to take the limit and see what happens. If it exists, then it's removable. If it doesn't exist, then it's not removable. Do you understand how to fix it in the removable case? Yes? Okay, good. So, I don't know why it's doing that. Okay, it's doing the same thing as the motion sensor stuff. Supposedly they had fixed it just when I called them, and then the last 2 weeks it's been okay, but now they're back to square one. Let me just turn this off and turn it back on. Anyway, you have examples there, so keep going. Work. Do the next one, 3 times tangent. The next function is 3 times tangent. Figure out the intervals where the function is continuous. Remember, step number 1, find the domain. That's your concern. After that, then you worry about taking limits and all of that. So we discussed the domain of tangents some like a couple of weeks ago. Anybody remember? How do we do this? How do we find the domain of tangent?
We rewrite it as sine over cosine.
Okay. And then? I mean, you have a fraction now. What do you do when you have a fraction? What is it?
That can't be zero.
The cosine cannot be zero. So your focus is what makes cosine zero. Okay, what makes cosine zero?
90 degrees.
And 90 degrees. And what else?
270.
And 270. Pi over 2 and 3 pi over 2. Remember, unit circle. Cosine, that's the x value. So you are on the y-axis. The points on the y-axis are 0, 1 and 0, -1. Yes? So that corresponds to pi over 2, 7, and 3 pi over 2. Yes? So pi over 2 with any coterminal and 3 pi over 2 with all the coterminals. Do you understand this? We talked about this some time ago. So remember, just if you see a fraction, you always have to concern yourself with the denominator. So naturally, your question, if you want to analyze tangent, you need to think about what makes cosine zero. And hopefully you think about the unit circle and all that. Okay? Right, so let's do that. So for number 3, we have our function is 3 times tangent. So remember, you either remember already what happens here. If not, then just rewrite it as sine over cosine. And then you understand that to find the domain, you need to focus on this guy, because you cannot divide by 0, right? So what is it that we don't want? What we don't want to happen is that cosine equals 0, okay? Does everybody understand that the solutions here are pi over 2 plus coterminals and 3 pi over 2 plus coterminal, or do I need to explain this? Yes or no? Okay. So from here it follows that x must be pi over 2 plus coterminals or 3 pi over 2 plus coterminals. Now remember, there is a clever way of combining these two guys, right? So instead of just focusing on pi over 2 and all the coterminals, going around and stopping always up there at the point 0, 1, and then just focusing on the point 0, -1, going around and stopping down there, you can jump back and forth by adding pi's. If you are here, you do plus pi, you are down here. Then you do plus pi again, you're back here, and so on. You understand this? So we combine these two families, and we just say pi over 2 plus k pi, okay? And then I'll tell you another way that we write that we like to write it. Remember here, k is any integer. This will allow you to go back and forth between these two. Okay. And now, typically, what we like to do here is we factor out here at 2k. We factor out. What do we factor out? I factor out pi, and then pi over 2. I'm going to factor out pi over 2, and then I'm going to have 1 plus. If I take out pi over 2, then this pi is gone. But because there is no 2 down here to take out, what is it that I need to do? So the k stays there, right? The k stays there. But certainly, I cannot leave this like this, because if I went to distribute my pi over 2, I'm going to have pi over 2, okay. But then I'm going to have pi k over 2. That's not what I want. I want pi times k, right? So what do I need to write here?
2.
2. So that when you distribute, it cancels with this guy. Do you understand this? So, and this is easier to read. So let me rewrite this. This means this is 2k plus 1 times pi over 2. What is this? What does this represent? This expression, 2k plus 1.
All odd multiples.
An odd number, right? So now it's easier to recognize this. So what makes cosine 0? Odd multiples of pi over 2. So 1 times pi over 2, 3 times pi over 2, 5 times pi over 2, 7 times pi over 2, and so on. So just put an odd number in here, and then you got yourself something that makes cosine 0. Do you understand this? So this is the domain of finding is all real numbers except the odd multiples of pi over 2. So you have to skip pi over 2, pi over 2, pi over 2, and all those. So this is, I guess, it's easy to remember this. If you want to remember something, it's easy to remember this and remember this. Okay? All right. With case and so that's the solution. That's what makes cosine of x equals to 0. So the domain is everything except those values. Okay? I want you to understand that this means, pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. And then also on the negative side, negative pi over 2, negative 3 pi over 2, etc. Okay? There's an odd number in front of the pi. It could be positive or negative. Okay? So f is continuous in the following interval. So that's all real numbers x such that x is different than 2k plus 1 times pi over 2, where k is any integer. If you want to write this in interval notation, it's a little bit more complicated because now we're talking about infinitely many intervals here, right? There are infinitely many pieces because you have to skip infinitely many points. But, just to give you an idea, you could write, let's see, pi over 2 to 3 pi over 2, right? Because you skip pi over 2 and then you have to skip 3 pi over 2 again. So everything in between is okay. Union 3 pi over 2, 5 pi over 2, union, and so on. And then let me go in the negative side, that way you get the pattern. And then I'm going to put one more. That will be negative 3 pi over 2, negative pi over 2. But, when we face something like this, it's easy to just write this one right here, which is the separated notation, okay? Just all real numbers x such that x is different than these values, okay? If you're writing in interval notation, this is what you do. Sometimes they tell you, analyze the function from 0 to 2 pi. Then that means you don't have to worry about all of these infinitely many values, and the only thing that you need to discuss is pi over 2 and 3 pi over 2, right? If you analyze the function from 0 to 2 pi, you just say it's continuous everywhere between 0 and 2 pi except pi over 2 and 3 pi over 2, right? Because the next time that is discontinuous is at 5 pi over 2. It's already outside of 2 pi. It's bigger than 2 pi, so we don't care. And then negative pi over 2, that's below 0. We don't care in that situation, okay? But because I didn't specify, we need to say everything. That's why I do this. Okay, so we know where the function is continuous everywhere except at these numbers because this is where cosine is 0. Now our job is to classify this continuity. So even though this is a nice way of combining, okay, so this is a nice way of combining all the solutions, but remember they came from two different situations, from two different families. The pi over 2 family, by family I mean pi over 2 and all its coterminals, okay? And the 3 pi over 2 families. So that means whatever happens to pi over 2, around pi over 2, the same thing will happen with, for example, 5 pi over 2, the pattern is plus 4. So pi over 2, 5 pi over 2, 9 pi over 2, etc., they all belong to that family in the top. So whatever happens at pi over 2 will happen to all of those guys. So let me make it. So pi over 2, 5 pi over 2, and negative 3 pi over 2, all of those, they have the same type of behavior. Around those points, the function behaves the same way. In particular, we have the same limit. And then similarly, if you focus on 3 pi over 2, the behavior around 3 pi over 2 will be the same as 7 pi over 2, then 11 pi over 2, etc. I'm saying this because now our job is to take limits to classify the type of discontinuity. You don't have to do this infinitely many times. We just take two limits, one at pi over 2, and this is going to tell me what happens in all the yellow things, okay? and then another one at 3 pi over 2, and you will tell me what happens at all the two. Do you understand this? Because they're the same. Okay, so f is not continuous at the following sets, at pi over 2 plus 2k pi, such that k is an integer. Now I'm separating this because these are two families and I will take two limits, okay? And also is not continuous at 3 pi over 2 plus 2k pi. So once again, the reason why I'm separating this is because the behavior around pi over 2 is different than the behavior around 3 pi over 2. It will turn out that at the end of the day, both of them will be infinity, okay? But the type of infinities are different. When you approach to the right at pi over 2, you will get one type of infinity. When you do it at 3 pi over 2, you will get the other, okay? So we're gonna figure that out. All right, so by the way, remember, usually whenever you have a fraction and the bottom becomes 0, if it's not removable, meaning if you don't have a hole, what's going to happen is, what you're going to have is a vertical asymptote, okay? And as you know, when you have vertical asymptote, you should not be taking limits from both sides, because the thing that happened above is going to happen. You're forced to look at side limits. Remember here, when you get here, then you're stuck. You know you will get, you should get some infinity, but which one is it? I don't know. I have to look at side limits. So because it's coming, it's a value that makes the bottom 0, then immediately you should be looking at side limits. So you avoid that step, okay? That complication. That's why I'm gonna take a side limit. Instead of just going straight to pi over 2, I'm gonna do it from the right or from the left, whichever you want me to do. Doesn't matter, okay? So let's see, let us analyze pi over 2. So let's look at the limit as x approaches pi over 2 of the function. And now tell me, what do you want? From the right or from the left? Left? Okay. So let's do it from the left. Again, it doesn't really matter, okay? So we are approaching pi over 2 from the left. I'm going to rewrite the function here. So I'm going to write it as 3 sine over cosine because it's easier to analyze it that way. We know that when we get close to pi over 2, sine gets close to 1, right? So the top is close to 3 because it's 3 times 1. And then the bottom gets close to 0, so we know this is some type of infinity. 3 over 0 would be some type of infinity, right? The question is, which one is it? All right, so let's see. So what do I write here? Do I write positive infinity or negative infinity? And the only way for us to know that is we need to know what's the sign of cosine as we do this. Because as you know, you are close to pi over 2, that means sine is positive because you are either in quadrant 1 or quadrant 2. That's our job. We need to figure out where are we, what quadrant. Depending on the quadrant, then we'll be able to control the sign of this function. Okay, so what do you know about x here? This means that x is less than pi over 2, right? So in what quadrant is this? Quadrant 1. So that means we are in quadrant 1. What do you know about sine and cosine quadrant 1? They're both positive. So what type of infinity do we have here? Positive infinity. If you understand this, if we would have done it from the right, that would mean that x is bigger than pi over 2. So what quadrant are we? Quadrant 2. So what does that mean? What does that mean about sine? Remember, do you remember where the trigonometric functions are positive and negative? So in quadrant 2, sine is positive. How about cosine? It's negative. So positive divided by negative is negative. So you will have negative infinity. Do you understand this? Okay. So anyways, the point is that this side limit gave us infinity. So in particular, the full limit is not going to exist, right? It's going to be either does not exist or infinity. In this case, it will not exist because to the right, we're going to get the other type of infinity. So, but just by looking at this, you know you have an infinite discontinuity. So that's an infinite discontinuity. And therefore, this family over here is non-removable. this limit that we got for pi over 2, the same thing will happen at 5 pi over 2, and 9 pi over 2, 11, and 13 pi over 2, and so on. Okay? So there's no need to look at all of those. Just with this one is enough. Now we repeat the same game with this one. So now we're gonna analyze 3 pi over 2. So let's do the limit. How do you want to approach 3 pi over 2? On the left? like approaching from the left. Always tell me left. There are more right-handed in the world. So, okay, so what's the answer here? What do we need to do at this point? So what's the top? When you take the limit, what's the limit on the top? Negative what? Negative 3, right? Remember, 3 pi over 2 sine is negative 1, right? So the top is negative 3, and the bottom?
0.
0, okay. I don't know why you guys seem like... Do you know what I'm talking about?
Yes.
Then why you don't answer? Like you don't seem sure about. I'm asking you little questions. What day is today?
Good question.
What day is today? Wednesday. And then number?
25.
Okay. So you know, I'm asking you simple questions. We have gone over these many times. All right, so with the top is a number, the bottom is 0, we are expecting here an infinity. Our job now is to figure out what infinity. And we know does not exist. I mean, it does not exist, but we know it will be an infinity because we're looking at a side limit. When you are not sure is if you look at the full limit, and it's because from either side your behavior could be different, and then you cannot pick one of the infinity, and you have to say it does not exist. Okay? But anytime that you look at a side limit, you either get a number or a type of infinity. There is no other choice. Okay? Unless you have a weird function, like the sine of 1 over x. Okay? Alright, but that's not this case. Okay, so now to decide the type of infinity, what do we need to do? What do we need to do? We need to know the sign of this function. And because this is a trigonometric function, to know the sign of this amounts to knowing what? The quadrant of the input, right? Yes?
Yeah.
Okay. What quadrant are we? What do we know about x here? X is less than 3 pi over 2, so it's quadrant 3. If you are a little bit confused on how to figure this out, just draw the picture. Okay? Here is 0, pi over 2, pi, 3 pi over 2, and 2 pi. If x is less than 3 pi over 2, remember, we are close to it, okay? So that means that it's somewhere here, right? And this is the angle that we're looking at. Do you understand this? Because remember, we're measuring, we are looking at positive angles. If this would have been a negative pi over 2, because instead of 3 pi over 2, you could talk about this and say negative pi over 2, but then you're measuring like this, okay? So your picture will be different. Do you understand that? But in this case, we're measuring positive, so you're getting close to 3 pi over 2 like this, okay? That's what it means to be less than 3 pi over 2. And you can see from the picture, we are in quadrant 3, okay? Because here in quadrant 2, you're too far away. Eventually, to get close, you have to come. And from the right, it will be something here on this side, and therefore it will be quadrant 4, right? It will be bigger. Okay, so the point is that this is in quadrant 3. And what do you know about sine in quadrant 3? Negative. What do you know about cosine in quadrant 3? Negative. So negative divided by negative, positive. Now, that's sine and cosine. And okay, and then 3 is positive. So the whole thing is positive. So positive infinity. Do you understand this? Also, if you want, you can say, oh, the top is a negative 3, right? And then the bottom is getting to 0, close to 0 with negative numbers. So negative and negative, positive. Many ways to think about it. All right. The moral of the story is that we also got an infinite discontinuity here. So in both families, we have the same type of discontinuity, non-removal. And this is, if you know the tangent function, this is precisely where we have all of these vertical asymptotes. There's nothing we can do about vertical asymptotes. We can remove holes, but not asymptotes. Okay? Asymptotes or gaps, that's too bad. We cannot fix it. Okay, questions? No questions? Okay. All right, so let's see. Now try number 4. It's essentially the same thing. It's just a little different, slight modification. Just threw a pi in here, but that's all. Let them work into it. Do you understand what to do in number 4? So what needs to be done here? So I don't want to know, don't tell me the answer yet. Just tell me what needs to be done. You see this problem? What do? You need to have a plan. What do?
You solve pi of x equals pi over 2.
No, don't tell me a solution.
You
What's the
just-
plan? What do you do?
The denominator can't be 0.
Okay.
So you have to make sure cosine isn't 0.
So the bottom line here is solve the equation cosine of pi x equals 0. Right? That's your job. Solve that little equation. Do you understand that everything else is okay? The top is a polynomial. So the top is continuous everywhere. The bottom is continuous everywhere because cosine is continuous everywhere. So the quotient will be continuous except where this guy is sitting. So to find continuity of this function, you just have to find when the bottom is sitting. So solve the equation. Your classmate kind of already told you what to do. It's essentially the same thing that we did here. Okay? The only difference is that instead of an x, what do we have inside the cosine? Pi x, right? So that means that here, instead of x, what you should write? Pi x. That's all for x. That's all it is. So for example, if you have cosine of whatever equals to 0, that means that this stuff must be either pi over 2 plus all its coterminal or 3 pi over 2 plus all its coterminal. There is no other choice. Those are the only choices, okay? If you have cosine of something equals 0, that means that something is either a pi over 2 or a 3 pi over 2. That's what it is. Or, of course, any of the coterminals. Do you understand this? And then, of course, if the stuff that you have in there is not just x, but something more complicated, then you need to isolate your x, like moving things around and so on. So if you have a pi x in here, that means you have a pi x here and a pi x here. But then you have to divide by pi, right? Solve for x, and then you will get your solutions. So the function is x squared plus 1 over cosine of pi x. I'm putting this example just to remind you of these techniques that you learned back in trigonometry, because I don't want you to not be able to do it if something like this comes up in the exam, right? It's essentially the same thing as what we just did in the previous exam. You just have to understand that here you already have the pi. So for example, you know that in the previous problem, what was the point that was giving you an issue? Pi over 2, right? That was making cosine 0. Do you understand this? Now, what would be the value corresponding to that pi over 2 that makes this 0? Just 1/2. Because you already have the pi in there. You just need to put the 1/2, or the 3/2, or the 5/2, or the 7/2. Do you understand what I'm saying? You already have the pi. You just need to put the coefficient that makes it 0. Okay, so what are the solutions?
X equals
Okay, and that amounts to what?
All multiples of 1 over 2.
Exactly, just odd numbers of 1 over 2. In other words, fractions of the form an odd divided by 2. 1/2, 3/2, 5/2, 7/2, 9/2, etc. Or -1/2, -3/2, -5/2, and so on. I mean, as I said, it's exactly this that we did here. Just remove the pi. Right? Just remove the pi from the picture, and what are you left with? 1/2, 3/2, 5/2, 7/2, and so on. Okay. All right. So good. So again, we just find the domain, and that will tell us the continuity. And to find the domain, we need to solve this equation. So remember, this means the stuff inside, I'm gonna already combine the two families. This is an odd multiple pi over 2, right? Which case any integer. I put the two families together, what we did above, okay? And then this means that x, I'm gonna divide by pi. So this pi cancels with this pi. So this would be 2k plus 1 over 2. In other words, solutions are fractions where the top is an odd number and the bottom is always 2. Right? So this is something, let me specify that this is something that we don't want. So f is continuous in the following interval. All real numbers x such that x is different than 2k plus 1 over 2, for a case an integer. Just to make it more clear, this is x such that x is not the following, so as 1/2, 3/2, 5/2, etc. Okay, you just have to avoid all these type of fractions for this function. Okay, and then essentially the behavior, what type of discontinuities do we have at all of these points? Will be exactly the same thing as what we did above, right? It's just instead of pi over 2, we're approaching 1/2, but still, the argument is still a pi over 2, right? So it's the same type of behavior we have. Now it seems even shorter the time the. All right, so do the last one. So the answer here is the type of discontinuities that we have at all of these points is non-removable, right? And the limit, you do it by taking the limit as usual. So write that down and then do the last example. Number 5. So just right here, similar to above, f has non-removable discontinuity at all of these points x, well, let me say, at points of the form 2k plus 1 over 2. What case of it? Okay, so the discontinuity there is non-removable. All right, so number 5. The last function was 3x plus 1 over x squared plus 7x plus 12. So when you analyze a rational function, the first thing is factor everything. So let's just factor everything, and then we can easily answer the question by just looking at it. Okay? Nothing to do in the top. How about the bottom?
X plus 3, X plus 4.
X plus 3, X plus 4. Okay, so don't give me interval notation. Just tell me in words. What's the domain? Everything except -3 and -4. Yes? So this function is continuous everywhere except at those two numbers, -3 and -4. Everybody okay? Now, what's going to happen at -3? What type of discontinuity do we have? Is it removable or not removable? What will happen to the limit? Remember, for rational functions, the only way you can get a limit in this situation is if you get cancellation, right? If you don't get cancellation, you will get a number in the top and a 0 in the bottom. Do you understand this? If you approach -3, regardless of the side, the top will be a number and this bottom is a 0. So you're going to get a type of infinity when you do a side limit. So not removable. Do you understand what I'm saying? My point is that by just looking at this, you can answer the question. Okay? And how about -4? When you get close to -4 from one of the sides, what's going to happen? Same thing. You're going to get one type of infinity because there's no cancellation. Remember, you know rational functions. What do we have at these two numbers, -3 and -4, for the graph of this function? We have vertical asymptotes. The asymptotes are the zeros at the bottom. You first need to simplify everything, and then whatever remains in the bottom, the zeros are your asymptotes. In this case, nothing simplifies, so you have two asymptotes, -3 and -4. That means the discontinuity there is infinite, therefore it's not removable. And do you understand this? Mm-hmm. So I'm trying to tell you this is not difficult at all. Okay? It becomes complicated when the function is, if I now throw in the timing here and I start doing a bunch of weird things, now it becomes a little bit more involved. But if it is just a rational function, it's pretty straightforward. Just factor, and you can see exactly what's going on. Okay? The domain is everything except whatever makes the bottom 0. Don't simplify. Then later, when you start to analyzing the discontinuities, if there is something that cancels, that 0, the factor that is gone, is removable. Right? If something doesn't cancel, then that 0 is a non-removable discontinuity. That's it. Okay? So f is continuous, all real numbers except -3 and -4. So let me write it like this. And remember, if you want to write in interval notation, we need to write 3 pieces, okay? -infinity to -4, union -4 to -3, union -3 to infinity. That's where it's continuous. And then at the points themselves, both discontinuities are non-removable. And f has non-removable discontinuity at x equals -4 and x equals -3. Are we okay with this? All right. Questions on how to determine continuity of functions given to you as a formula. It's basically find the domain. That's all it is. Okay? So you're back to college algebra if you want. Because that's what you used to do in college algebra, left and right. Hopefully. Finding domain of functions. Okay, so still these functions are very simple in the sense that I have now, for example, what happens if I were to throw in square root in here and that kind of stuff, or square root in here and that kind of things. Okay, so if I do that, what happens is that we are creating now a composite function, a composition. This is a composition of the square root with this fraction, right? This one is a composition of the square root with this sum. So do we have something that allows to deal with composite functions? And luckily, yes, we do. Exactly the same way that we have these nice properties that when you do the basic, when you do the basic operations, you still get continuity. Well, same thing applies to composition. If you take the composition of two functions, you obtain of two functions that are continuous, you obtain a continuous function. Okay, so you don't lose continuity when you do the composite operation. So let me write that down. So theorem, basically the statement is the composition of two continuous functions is continuous, of course, on this domain. Okay. So this is the basic idea. Let me write down the more formal statement. So more formally, what I'm saying is, if G is continuous at x equals a, and f is continuous at G of a, okay, then the composition of f and g, remember this is f of g of x, is continuous at x equal a. The reason why I have to write these things is because remember there are two functions here. There is an inside function and there is an outside function, right? When you do composition, and then the thing is that the x of g, the input of g is not the input of f, right? The input of f is actually the output of g. So we need to make sure that two things happen. We have to make sure that g is continuous at the input, but then f is also okay with whatever output g gives you. Okay? So that's why you see this line, g has to be continuous at a, and f has to be continuous at g of a, the output. Okay? But anyways, when you look at the composition, you can think of this as a function of x, right? The original input. And what we're saying here is that when this condition is satisfied, then the composition is fine and will be continuous as well at the point x equal a. And for example, this now allows to deal with other functions. For example, say f of x equals natural log of 3x, f of x equals the square root of x squared plus 1, or f of x equals tangent of 1 over x. All of these are continuous from their domain. Why? Because these are compositions of continuous functions. This is the composition of the natural log with the function 3x, right? So 3x is continuous, the natural log is continuous on its domain, okay? Therefore, this composition is continuous on its domain. Continuous on their domains. Same thing here. So here square root function is continuous on its domain. This one is continuous on its domain, so the composition is continuous. Okay? And same thing here. 1 over x and tangent, they are both continuous on their domain. So the composition is continuous. Okay? On their domain. So you want to figure out continuity here, find the domain. So let's see, what's the domain of the first one? Let's write down that quickly. So for 1, what's the domain? Just to practice this. How do you find the domain of a natural log function? How does the natural log function looks like? I mean, remember, domain is what is it that you're allowed to plug in. If you don't know immediately, then just think about the graph. You know the graph of the basic functions. How does ln looks like? Think about the x's that you can plug in. Can you plug in a -3 here? then what's the domain of a natural log? What can you plug in? Only positive stuff. You think about the graph, everything is happening to the right of the y-axis. There's nothing to the left. Remember, ln looks like that. Yes? There is nothing to the left. This is the graph of ln. So, for the domain here, you have to make sure that 3x is greater than 0. Because you cannot do ln of something negative. And this means that x itself must be positive. So, where is this function continuous? On the interval from 0 to infinity. You okay with this? All right. Questions? Okay, let's do number 2. Number 2 is square root of x squared plus 1. What's the domain of this? Very good. Why? So you cannot have negative numbers inside the square root, right? But now the question is, x squared plus 1, is this ever negative? No, this is always positive, right? If you think about it graphically, that's your parabola shifted up 1 unit. Or algebraically, x squared, regardless of x, is either 0 or bigger, and then you're doing plus 1. So there's no way you can get a negative number here. Do you understand this? So you can plug in whatever you want. This will be positive, and therefore you will be able to take your square root. So domain is all real numbers. So it's continuous on the entire real line. Because it's a composition of two continuous functions. And for number 3, what's the domain of this? So what do we need to worry about? So we need to worry about 0 itself because of the 1 over x, right? What else do we need to worry about? The cosine being 0 at this expression, right? Now, can you see when would the cosine be 0? Just by the experiences from before? Very good. You just have to flip the solutions from before. Remember, this 1 over x just means flip the input. Before, the problem was a pi over 2, for example. Now, what's the problem? A 2 over pi. Right? It was the same solutions that we got from before, just flip them. Do you understand what I'm saying? If you put pi over 2 here, that's okay, because this becomes a 2 over pi, and tangent of 2 over pi is fine. Now, if you put a pi over 2 down here in x, that becomes, no, sorry, if you put a 2 over pi down here in x, then it becomes a pi over 2, and there is an issue. So that's why we need to flip all the solutions that we have from before to find all the issues. So, again, so I'll say for the domain, so what is it that we don't want? So we don't want several things. So first, we don't want x to be 0. That's something that we need to exclude. That's because of the 1 over x. And second, we don't want the stuff inside the tangent to be odd multiples of pi over 2. I'm not going to redo the whole computation. This is the same thing that we did above, okay? But then, this is 1 over x, because that's the stuff inside the tangent. Well, split. So that means x is 1 over this, which is 2 over, okay? So that's 2 over pi when k is 0, 2 over 3 pi when k is 1, and so on, okay? So here, this is referring to 2 over pi, 2 over 3 pi, 2 over 5 pi, etc. Okay, that's what that's referring to. So that's what we don't want. Everything else is fine. So this is continuous on the following set, all real numbers x, such that x is different than 0, and x is different than this collection. Questions on this? Again, I didn't do much calculations because we already carry the calculations above. Okay, the 1 over x over here is like the x that we had before, or the pi x that we had before, when resolving cosine of x equals. All right, and the reason why we don't have to worry about anything else is because we have that theorem that says composition of continuous is continuous on the domain. So just find domain and you're good to go. All right, so we have not done, notice that everything that we have done now deals with only a concrete formula. If you're given a concrete formula, it's really just a domain question. Now, typically, the interesting question about continuity is when you have piecewise functions, okay? Because when you have a concrete formula, full formula, it's just domain. There is nothing more to worry about than the domain. But now, when it's piecewise, it's no longer the domain anymore, okay? You have to investigate, is the domain for each of the pieces, but also then you have to investigate what happens at those points at which the function changes formula, okay? Because you may have gaps, that kind of stuff happen. So let's do some examples on that. Okay, so more examples. Describe the intervals on which each function is continuous. And then let's do absolute value of x minus 5 over x minus 5. And then let's do sine of 1 over x if x is different than 0. And then 0 if x is equal to 0. Okay, so the first one, how do we do this?
We have to make two cases. Absolute value.
Okay. So number one, you can treat it the same way that we're doing it before, using the rules. Let's see. This is a quotient of two functions, right? I mean, it's true that the absolute value function is a piecewise, but only if you want to actually take the limit. But here they didn't ask you to classify the discontinuity, so you don't really need to take limits if you don't have to, okay? So if you can get away with the theorems, then you're good. So in this case, we have a fraction. You just need to worry about continuity of the top and the bottom, right? So let's look, the bottom is easy. The bottom is continuous, right? X minus 5, that's a line. Do you understand this? Now let's look at the top. What's the top? That's a composition, right? That's a composition of what function? What's the outside function? The absolute value function. What's the inside function? The x minus 5. X minus 5 is continuous. What do you know about absolute value? It's continuous, right? You can draw the absolute value without lifting your pencil. There's no problem with the absolute value. So composition of continuous is continuous. So the top is continuous, the bottom is continuous, therefore that fraction is continuous on its domain, right? So if you want to find continuity here, you just need to figure out domain of this function. What's the domain of this function?
X is not equal to 5.
Okay, so all real numbers except 5, right? Everything else is fine. Do you understand this? That's why I gave you all that list of theorems, so you don't have to actually start computing stuff if you don't have. Okay? Most of the time, you will need to compute things if you have a explicitly written piecewise function, or if you have a very complicated function that finding the domain itself is not straightforward. And then you need to do some calculations, like before we needed to solve cosine equals 0 and those things. But here, you can just look at it and see what the domain is. And that's all you need. So solution for the first one, I mean, I'm gonna write a couple of sentences, but so this is just note that the absolute value, that y equals absolute value of x minus 5 is continuous, and also y equals x minus 5 is continuous. So f is continuous on its domain. Which happens to be all real numbers let's set 5. And if we are asked to give this in interval notation, how do we write this in interval notation?
Negative infinity to 5.
Uh-huh.
And then 5 to positive.
Union 5 to positive infinity. And parentheses everywhere, right? Okay. Questions? And then if you are asked to identify, so it's not continuous at 5, right? So if you're asked to identify the type of discontinuity, you have to take the limit. And as you know from before, what's going to happen at this limit when we approach 5?
0.
Well, we get 0 over 0, right? And so you have to do side limits. And what was the experience that we had from before? From the left, you get one value. From the right, you get another value. So the limit does not exist. Remember, this function is always either 1 or negative 1 all the time. Because the top and the bottom, they have the same value in absolute value. It's just that sometimes the bottom is positive, sometimes the top is always positive, but this could be positive or negative depending on x. If it's less than 5, to the left of 5, this is negative, so you will get a negative 1, right? If it's bigger than 5, so to the right, this is positive, so you're going to get positive 1. So you have a jump discontinuity of 5. Yes? Okay. All right, how about the next one? Okay, let me say here, at x equals 5, we have a non-removable discontinuity. And right here, jump. So you know what that, okay? The next one was sine of 1 over x. If x is different than 0, and then 0 if x is 0. Okay? What do we do here?
Should we find the limit of the first equation and make sure it equals 0?
The limit of what? Okay, but why? Remember, your job is to analyze this function and tell me where it's continuous. So what's the first thing that you do when you're analyzing continuity? What do you look at? You have to look at the domain. What's the domain of this function? All real numbers. So that means you need to worry about all real numbers now. So you need to make sure that you can take limit for all real numbers and that the limit coincides with the value of the function. Okay? So naturally, whenever you have a piecewise function, this forces you to split your problem into different cases. What are the cases here? So 0 definitely is a case that you need to analyze on its own, right? Then what are the other two cases? To the left of 0, to the right of 0. Do you understand this? Those are the two cases. So the other two cases. So I'm going to analyze here 3 cases, because I have to analyze all numbers, but I'm going to first, I'm going to make my life easy. So less than 0, bigger than 0, and then equal to 0. Okay? And then let's see what happens. So remember, this is the interval from negative infinity to 0. What's the formula for a function in this case? Sine of 1 over x, right? Because when x is less than 0, in particular, it's not equal to 0, right? So you should be looking at the first formula. Do you understand this? So the way you read that function is, if the input is not 0, if x is not 0, then look at the formula sine of 1 over x. Only when the input is 0, your output is 0. And that's the way you read that formula. So in this case, because x is less than 0, we're looking at the first formula. So this is our function. Yes? Now, what is this? This is a composition of two functions. Therefore, this will be, and each function is continuous in the domain. Because 1 over x is continuous on its domain, sine is continuous on its domain, the composition is continuous on its domain. Right? So we need to find the domain of this function. What's the domain of this function?
Order numbers is at 0.
Exactly, because sine has no issues, right? You can plug in whatever you want into a sine function. Do you understand this? The only problem here is 0. Are we concerned about 0 in this case? No, we are to the left of 0. We are less than 0. You are looking at negative numbers only in this case. Do you understand this? Our concern is not 0. We will worry about 0 later. We are not worrying about 0 right now. So this is a fine function. This is a fine function. The composition is fine. So this continues. Nothing to do. How about the other case? Here we are on the interval from 0 to infinity. What's our formula? So you always need to ask yourself, what's my formula? Otherwise, you cannot analyze the function. Okay? So what's the formula to work with? The first one. Once again, x is not equal to 0 here, right? We are only looking at positive x's. So we are still in the first formula. Remember, the way you read this is, if you are not looking at 0, that's your formula. If you look at 0, then the output is 0. Okay? Once again, what happens here? What's the conclusion in the second case? Continuous. Because the two functions are continuous in that piece. Okay? So what remains is this one. Now, this is a point. We're no longer looking at an interval. Now we're looking at a point. When you have the point, you have to go by the 3 rules. Okay? Continuity at a point. What are the 3 rules that we need to check? What's rule number 1? Is the function defined? Which means, can you plug in? Rule number 2, does the limit exist? Rule number 3, in case that 2 is okay, then rule number 3, is the value of the limit the same as the value of the function? Okay? If you say yes to the 3 questions, then okay, it's continuous. If one of those fails, it's not continuous. Right? So because this is a point, then the first thing that we need to ask ourselves is, can we plug in 0 into the function? So can we plug in 0 into the function? What's the output? 0. So we're good there. Go to the next one. What is it? The limit. So we need to ask ourselves, what about the limit? Does this limit exist? Right? So what do you think? Does the limit exist for the function? Why?
Goes from negative 1 to 1 nonstop.
Why?
So the function sine of 1 over x.
Why are you looking at that formula and not the value 0?
Because the limits, right?
Uh-huh. I want to make sure that you understand what. So why? Why do you look at the formula and not the value 0?
Because that's the side limits.
Because we
Around
care
0.
Because when you take a limit, you only care about what happens around the point, not at the point. So when we write limit, remember x is not 0. X is very close to 0, but in particular it's different than 0, right? If it's different than 0, what formula do we have here? Sine of 1 over x. And what do you know about that function when you approach 0? It does not exist. That's the one that becomes crazy when you get close to 0. Because the argument goes to infinity, and or either positive or negative infinity, depending on what side you are approaching. But regardless, because sine is a periodic function, it just keeps on giving you every single value between 1 and negative 1. So it doesn't get close to anything specific. Yes? So that's the full story. Okay, so to answer this question, technically what you need to do is, okay, try to compute it. When you try to compute this, you need to have a formula for this. You need to know what to write in here. Well, we are here. Typically, if you have a side function, a piecewise function, you should look at side limits. Depending on the side, is the formula you use. But here, this is telling you that on either side of 0, you have the same formula. That's what this means, right? Less than 0 or bigger than 0, the combination of those two is what this means, different than 0, okay? On either side is the same formula. If I wanted to have a third formula, then this would be probably, I don't know, less than 0, then add 0 to this, and then bigger than 0 will give you another formula. If that happens, you do have to look at side limits, to the left and to the right, okay? But it's not happening here. So that means if you get close to 0, in particular, you are not equal to 0. X is not 0, okay? It's close, but it's not equal to 0. So we use the formula. G equals sine of 1 over x, and as you know, the limit does not exist. It's not even infinity, that just does not exist, doesn't get close to anything. So the answer here is a big no. So at this point, we stop, we don't even need to go to condition number 3, and we deduce that the function is not continuous. Moreover, what type of discontinuity do we have? This is, what is it? Non-removable. Okay? Because the limit does not exist. Questions? So where is this function continuous? So where's the function g continuous? So all real numbers except 0, right? So g is continuous on negative infinity to 0 union 0 to infinity. And at 0 we have a non-removable discontinuity. Questions? Okay, so all right, so we're good there. Let's do another type of examples now. See, okay, here I had another function. Forgot to write. How about this one?
Is e part of the exponent?
This x squared times e to the sine of 1 over x. Okay, so what's the domain of this function? Or real number. So what does that mean? What do we need to do? We have to split this into 3 cases. What are they? Less than 0, bigger than 0, and 0. Right? I mean, this is automatic. You see this as something that you do automatic. Even if you have no clue what to do after that, but at least you should begin that way. Okay? And then as you start writing, hopefully the problem is going to guide you on what needs to be done. Okay? And why do we have different cases? Because the domains are real numbers and this is piecewise. So you need to split this into cases so that you know what formula to pick to work with. Okay? All right. So let's do it. Okay, so 3 cases. X less than 0, x bigger than 0, and then x equal to 0. Okay, x less than 0. What's our formula? First one. What can we say about this? Why? Okay, and then why is this continuous? Because, just use the properties. This is a product of 2 functions, right? If we manage to show that the 2 functions are continuous, then the product is continuous. Yes? How about the first function? Is it continuous? X squared. Yes. So the question is the other one. What's happening in the second function? It's a composition. It's an exponential. It's actually a triple composition, right? It's an exponential with a sine, and a 1 over x inside. Do you understand this? The outer function is exponential, then the middle function is a sine, and then the innermost function is 1 over x. Do you see that? Now, all of these functions, what do we know about those for x less than 0? They are all continuous. 1 over x is fine, sine is fine, e to the x is fine. So when you put them together as a composition, it's fine. So this one is continuous, the product of two continuous is continuous. You need to know how to justify this, because if I ask you, why is it continuous, then you need to write the sentence that I'm telling you. Do you understand what I'm saying? That's why you have those theorems, okay? All right. And there's no computation to do here. Just use the theorems. It's a product of two continuous functions. All right. Similarly, on number 2, because x is bigger than 0, in particular is different than 0, so we have the same formula. And once again, this function is okay, because the only issue here is 0. So it's continuous. All right. So now it's 0, because this is a point, we need to analyze 3 steps. Value of the function. What's the value of the function at 0? 0. Number 2, limit. So does the limit exist? Does this limit exist? So now we do need to compute the limit. So how do we compute this limit? So our job is to find limit as x approaches 0 of x squared times e to the sine of 1 over x. How do we find this limit?
Is it 0?
So how do we find this?
Would you plug in 0?
Okay, if you plug in 0, what happens? I mean, you always try to plug in. That's the first thing that you always do. What happens if you plug in 0?
0.
What do you mean? Where is this infinity coming from?
Sine.
But what happens to that term, sine of 1 over x, when x approaches 0? It does not exist. It doesn't get close to anything. So e to whatever that is doesn't get close to anything. Right? So we're doing 0 times something that we don't know what it is. Something that doesn't exist. So we cannot say, I mean, it's not clear what happens. In other words, just plugging in is not going to do the job for us. You understand this? And even if this was an infinity, 0 times infinity is an indeterminate form. The same way that 0 over 0, you cannot decide anything, you need to do something. Okay? There are 7 indeterminate forms. We have encountered 0 over 0, infinity over infinity. There are 4 more, there are 5 more. That's 0 times infinity. Then you have 1 to the infinity, 0 to the 0, infinity to the 0, and then infinity minus infinity. Okay? We're going to learn how to deal with all of those eventually. Right now, we only have 0 over 0, infinity over infinity. And we saw the 1 to the infinity in the definition of e, the limit 1 plus x to the 1 over x when x approaches 0. Okay? The point is that here, this piece here does not exist. So you cannot use the rule that the limit of the product is the product of the limits. Okay? Because if you could use it, then, okay, this is 0 times whatever, then that would be 0. But, well, we cannot use that rule because this part doesn't exist. So how do we know what happens here? So you need to try something. Factoring doesn't work for us, right? I mean, there's nothing to factor here. Conjugate, that's not going to work. What other techniques do you know to compute limits? This is essentially something that you may not want to graph. So what other techniques do you know? And remember, no numerical approximation. I mean, if you are in real life and you really want to get an answer, then if you don't have any tools, then you just go ahead and do your table of values. But, but then you only have an estimate, a guess. We want to be sure. So what do we do? What other technique do we have at our disposal? but still you're gonna have the same issue, right?
Squeeze theorem?
The squeeze theorem. That's another option that we can use, right? Squeeze theorem. Now, can a squeeze theorem be used here? Remember, the job for squeeze theorem means you need to find two functions, one that's less, one that's bigger, that bound this function. And if those two have the same limit, then the one in the middle is forced to have the same limit. Yes? Now, when is squeeze theorem useful? I said all of this when I was talking about it. As I was explaining the examples in the video, I was telling you when this is useful. When you may want to use squeeze theorem. Every time that you see sine and cosine, squeeze theorem should be in your mind, unless you can plug in and do something, okay? But if not, squeeze theorem. Why? Because there is something that we know a priori about those two functions. What do we know about sine and cosine? Yes?
They're periodic.
They're periodic. What else?
They're set between 1 and 3.
Exactly. So when you see sine and cosine, you know whatever is going on inside those functions is not going to go below -1 or above 1. So you have an inequality to begin with right there. Then you just need to work with that inequality to build the function that you are interested in. Okay? Sometimes this helps, sometimes it doesn't. Like as we saw the sine of x over x, it didn't help us because we got two different infinities, and then we need to do all the geometric thing, etc., right? But let's see here, is it going to help us? Well, let's try it. So I'm going to try squeeze theorem. The point is that when you see this, you need to decide this on your own. Nobody's going to tell you do the problem by using squeeze theorem. So what you do is you run through all the techniques that you know. Try plugging in. Oh, doesn't work. You know, what's happening? Can I do some type of simplification, factoring, or something like that? There's nothing to do here. Squeeze theorem. That's another choice, another tool that you have. Okay? And then, because I see the sign, this is a hint that I may want to use this. Let's see. What do you do? Well, we start with this. So I know that sine of 1 over x, I don't care what happens with x. Of course, and we are away from 0. Remember, x is not equal to 0, so this expression makes sense. Whatever x is, this is always between -1 and 1. Now, my job is to build inside here that function, with the hope that to the left and to the right, I'm going to get two functions with the hope that when I take that limit x approaches 0, they go towards the same value. If they do, then my function will go to the same place. Okay? So, let's see. Now, what's the next step? What should be the next function that we build? Now, we want the e to show up, right? Then x squared is the last one. Why? I could multiply by x squared now, but then how do you get the e? You already have the x squared in the middle. You have to think of this as a little game, okay? You have the sine of 1 over x. Now, what's the next step that you should do to build that function? To e to the power. And then, times x squared. You understand this? If you multiply times x squared, then how do you get the e in there? There is no way. You cannot just do e to half of the expression. That's not valid. There's no mathematical operation that allows you to do that. Skip one and do the other. Okay. So after we do this, the next thing is that we should do the exponential. So I'd like to do exponential. Now the question is, if I do this, what happens here and what happens here? And will this remain? So I guess the question is, if I exponentiate everybody, right? I have this, I can say, oh, exponentiate everybody. Okay, but does this stay the same, or do I need to flip something, or what happens? So I'm doing this to remind, if you never saw this, so as you have it in mind. When you use a function and you want to see what happens with an inequality, okay? The question where the inequality stays or flips is a question about the monotony of the function that you're using. Monotony means increasing or decreasing, okay? If a function is increasing, what does that mean? What does it mean for a function to be increasing? Do you know what increasing is? What is it? What is it? Just say it. It's okay. Say it.
It goes towards the top right.
It goes up, right? When you graph it, it goes up. What does that mean mathematically? So let's draw a picture. I mean, I'm drawing the exponential picture, but it doesn't have to be a exponential picture. If a function is going up, how do you describe this mathematically? What do you mean positive?
It's increasing.
Yes, but then this one is not increasing. This one is negative, but it's increasing, right? And how about this one? It's always negative, and because it has horizontal asymptote, but still increasing. Increasing means that the graph is going up, right? Now, how do you describe this mathematically?
The limit at infinity is greater than the limit at negative infinity.
Yeah, but for example, in pre-calculus, but how is that going to help you with, for example, you know, increasing, decreasing from college algebra, there was no notion, there was no notion of limit at that point. So how? I mean, the limit at negative infinity may not even exist. Think about the natural law. You know, it's still increasing, but there is no limit at negative infinity. You have to make sure that we get something that works for every situation, right? Definition is something, now this is philosophy, but when you define something, you have to make sure that it always works, right? Like, it covers all possible situations. So what all these cases have in common? The graph is going up. So the question is, how do you say mathematically that the graph is going up? What does it mean to go up? First of all, it means that you look at graph from left to right. Because if I look at it from right to left, it's going up. Yes? If I understand this? So to go up means that as you go from left to right on the x-axis, what happens on the y-axis? You go from bottom to top. Mathematically, how do you say that? What does it mean to go from left to right? Pick a point here, pick a point here. x1, x2, with x1 less than x2. Right? If x1 is less than x2, then what can you say about the y values? This is your y1, this is your y2. This is f of x1, this is f of x2. What can you say about y1 and y2? Yes?
Could you just say, like, as x values increase, y values increase?
Exactly. And so how do we say that mathematically? I'm just telling you.
Slope is positive.
Simple than that. If x1 is less than, remember, our job is to say something about the inequality, so don't lose inequality. If x1 is less than x2, what can you say about f of x1 and f of x2? F of x1 is less than f of x2. In other words, if your function is increasing, it respects the inequality. It doesn't flip the symbol. Because if this input is smaller than this second input, then the output of the first one is still less than the output of the second one. If your function is decreasing, it's the opposite. It flips your value. Because the smaller the input, the bigger the output. If your graph is going down, what happens? If you have a graph that goes down, what happens? The smaller the input, the bigger the output. So what's going to happen is that if x1 is less than x2, then f of x1 is bigger than f of x2. That's in the decreasing case. In the increasing case, if x1 is less than x2, then f of x1 is still less than f of x2. In other words, if a function is increasing, when you apply it to an inequality, it doesn't affect the direction. If your function is going up, it's not going to affect the direction. If your function is going down, it will affect the direction. It will flip it. If it's less than, it becomes greater than. Do you understand this? For example, 2 is less than 3. What happens if I do 1 over x to those inputs? How does 1 over 2 compare with 1 over 3?
Bigger.
It's bigger. So 2 is less than 3. But then if I do 1 over 2, right, I apply the 1 over x function to this inequality. What happens to the inequality? Do I still keep it or do I need to flip it? I flip it. Why? Because 1 over x is decreasing. It's going down, so it flips. How about the square function for positive values? 2, let's see, 4 is bigger than 2. If I square them, what do? Do I keep the direction or do I flip it? I keep it. Why? Because the square function is increasing on the positive side, so it respects inequality. Moral of the story. Here we are applying the exponential function, so we need to know what happens to the symbols. We know that e to the x is increasing, therefore the symbols remain. Okay? So if -1 is less than this, then e to a -1 is going to be less than e to whatever this is. Okay? And same thing on the other side. All right, so again, this is pre-calculus stuff. Okay? So let me just finish this. Erase this guy. So make sure, I'm gonna do more examples for Friday, so make sure that you watch the video on Friday, okay? Because those examples are gonna be important for the exam. Just I was not expecting to, to spend so much time on this. Basically, let me just write here, f increasing means if x1 is less than x2, then f of x1 is less than f of x2. Okay, that's the definition. All right, and then the only thing that matters, the only thing that we need to do now is multiply by x squared. So that means now that x times e to a -1, I don't have to worry about flipping anything because x squared is positive. Okay. If it was just x, then you have to split into two cases. Less than 0, bigger than 0, because. And by the way, e to a -1 is just 1 over e, so let me write it like that. Okay, so this is our inequality. Our function is between these two guys. Now, at least we found a lower function and a higher function. The question is, do they work for us? Well, let's take the limit. What's the limit of this as x approaches 0? 0, right? It's 0 over e, which is just 0. And what's the limit of the other one? The outside function? 0 as well. So what can we say about the middle function? Better be 0, right? By squeeze theorem. So by squeeze theorem, we get that the limit as x approaches 0 of x squared times e to the sine of 1 over x equals 0. Okay? So the answer to this question is a yes. And moreover, we know the limit is 0 and equals 0, which is the same as number 1. So the answer to number 3 is fine. Limit as x approaches 0 of our function g. Did I say g or h? H. Of our function h equals 0, which is h of 0. So h is continuous at 0. Okay. So moral of the story: this function is continuous everywhere, right? Less than 0, bigger than 0, and it was also continuous at 0. So h is continuous on the entire real line. Okay. Questions? No questions? Okay.